Okay, so you saw this in the last chapter or stuff like that. If you apply a force that is constant on an object and it moves through a displacement s in a straight line, the work done was F dot S. F cosine theta S, the component of the work along the displacement times S. Okay, and then then you generalize, since you're calculus experts, we generalize this to the case when the force was changing, and all you had to do was calculate the x component of the force. So for each little displacement, calculate the x component of the force, so we called it fx, so a function of x, multiply it by the small displacement, add it all up, and that was the work done. This was still traveling along a straight line. Okay, and then you weren't happy with that, and so we said, okay, we'll allow you to go on a general trajectory. Okay, and the work done was this line integral. Okay. In general, this line integral is hard to do. Okay, so here's from your initial point to your final point. So for instance, if you are driving around in the city and you try to calculate the work done by your car engine, that would be a hard thing to do. You push your cart around in a supermarket, that would be a hard thing to do. It turns out that this line integral is easy to do for a few forces. It turns out that this line integral is the value of a function at the final point minus the initial point. And we put a negative sign for convenience. There's a couple of things about this thing. In the answer, something is missing. What is missing? I mean, this is the correct answer, but I'm sorry? No, this is a definite integral, so that's not. See, in this thing, this function depends only on the final point and the initial point. It doesn't care how you got there. So what we are saying is there are some forces for which this line integral gives you the same value on this path, on this path, on this path. Okay? Did you guys understand that? So that's a fairly neat thing. So those special forces are called conservative forces. Yeah. Work done, and what is the defining feature? Work done by these forces is path independent. Yep. And so for such forces, we can define a potential energy function. And that's that function. Okay? So the work done by these forces is negative of change in potential energy. Yeah. Well, how many of these kinds of forces are there? It turns out that there's gravity, the spring force. These are the only two forces that you'll see. And next, if you do physics 2, then you'll see the electrostatic force. Okay. Those three forces. But this is important enough, that convenience is important enough, and that concept is important enough that we give it special names and all that kind of stuff. Okay. Again, what is the great thing about conservative forces? This line, the work done is path independent, and so the line integral is very easy to evaluate. It's just that the difference change in that function. Okay. All right, so let's look at how this thing shows up. Okay. So that's where the title comes from, potential energy. Okay. That is the function you use to get the work done by these forces. And what are the three conservative forces?
Gravity, spring force, electrostatic.
And electrostatic. Okay. So we'll talk about them. So what does that mean? Okay, so what would that mean? So like I said, the path independent of the force. Let's say this was a frictionless slide. And you start from here and you come out here. If the slide were frictionless, the speed at which you come out would be independent of the shape of the slide. That's what that would mean. Okay? So then you would decide how to design your slide depending on what is the most exciting shape. Okay? All right. Of course, for friction forces, the work done depends on the path taken. For non-conservative forces, the work done depends on the path taken. And in general, that integral is hard to do. Okay. So, what are the non-conservative forces?
Friction.
All the others except for those three that you named. Okay. Friction forces, your car force, the force you're applying on the ground when you walk, and all that kind of stuff. Okay. So there are more non-conservative forces. Okay. You guys understand? Okay, so that's what this chapter is about. All right, well, why do we go to so much trouble? Here's the deal. Okay, so let's say you're playing ball, okay, and when the ball is in flight, let's say you can ignore air resistance. Then the only force that is doing work is gravity. Okay. And the work done by gravity can be accounted for by something called gravitational potential energy. Okay. So it turns out that the kinetic energy plus gravitational potential energy at every point is the same. So, and that's the neat thing about it. Potential energy plus kinetic energy is constant. And we love to do that in physics. You'll have a complicated motion, and we would like to, stay complicated. Okay, you have a complicated motion, and we're always looking for stuff. Hey, is there anything that's constant in this motion? Okay. So, going back to this guy, so for this complicated motion, you'll just see if there is no friction, potential energy plus kinetic energy is constant. Okay, irrespective of the shape of the slide. Okay, so if this is a frictionless roller coaster, this is showing you this is the kinetic energy. So as you're climbing up, you're slowing down. If you are just given a push, and then as you come down, the kinetic energy increases. This is potential energy. The sum of those two, you see, is constant. Okay. And no matter how the slide is shaped, as long as it's frictionless, the total energy, kinetic plus potential energy, will be constant. And that's what we like to say. Okay. All right. So work done by conservative forces, that line integral, okay, is path independent, is just the negative of the change in this function, and this guy is called the potential energy function. Yeah. Okay, so what are the two conservative forces that you've already met? I'm sorry? And spring force. So we'll give you the potential energy function for gravity and spring in a second. That'll be your job. Okay? So I'll just show you the expressions and then I'll derive them to you. Okay? Oh, actually, so for gravity, mgy, that's this potential energy function. Okay? Y is the vertical distance measured from a reference point. Okay? And upward being positive. And the spring potential energy is 1/2 kx squared. What is k? Spring constant. What is x? That's how much you stretch or compress the spring. Okay? So those are the potential energy function. All right. Why is that so good? Okay, so let's say here's a spring, here's the equilibrium position, and then you messed with the spring, you pushed it around, and there's the initial point, there's the final point. Along that path, if you ask how much work was done, the work was done was minus u final minus u initial, where there's the u function. Very easy to calculate the work done by the spring. Okay. All right. So, you guys understanding this? I'm not rushing through, am I? Okay. All right, so now we'll calculate the spring potential energy first. Okay. Okay, the work done by conservative forces is delta U is U final minus U initial. So U final minus U initial is equal to minus the work done by that force. Okay, so that's what we've written. Change in potential energy is negative of the work done, and the spring force, okay, so that's in 1 dimension. Okay, and this is in 3 dimensions. Okay, right. We'll calculate. Okay, well, we're going to calculate the gravitational potential energy first. Okay, so work done by gravity is negative of change in potential energy. Okay, so here's the setup. There's the gravitational force. The gravitational force on an object is pointing in this direction. There's the magnitude of the force. J hat is a unit vector upward. So the magnitude of the gravitational force is that. And then we're going to travel along. For now, we'll just travel along the y-axis. Okay. So there's dy j hat. The work done is, remember, this for a general trajectory, there's the force and there's dy. We are just going to travel along the y-axis. J dot j is 1, and so the work done is just equal to minus mg dy, initial to final point. Well, mg is constant, so we'll pull that out. So, and that's equal to minus mg dy. Integral of 1 is just y, so it's minus mg y initial to final point. And that's this guy. So negative of mg y final minus mg y initial. And there is u final and u initial. So gravitational potential energy is mgy. Okay. Okay, so now let me say something. Okay, so this is the gravitational potential energy. In this derivation, what did we assume? G was constant. You pulled it out of it. Okay. Is G constant?
Only at Earth's surface.
So G is constant. Very good, my friend. G is constant as long, so here's the radius of the Earth. Anybody know the radius of the Earth?
6,400 kilometers?
Very good, 6,400 kilometers, 4,000 miles. Okay? So as long as you jump small distances, small compared to this, then G is constant. Okay? So even we'll let you even jump 40 miles. That's 1% of the radius of the Earth. Then we'll say G is constant. Now you start jumping 4,000 miles, G is not constant anymore. Okay? So then we'll have to give you a new expression, and we'll give that to you in chapter 13. Okay, so as long as you're throwing rocks and footballs and all that, this is good. Okay. All right, so now we've given you the expression for gravitational potential energy. Now we'll give you the expression for spring potential energy. Okay, okay, again, the work done, here's the spring force dx, and that should equal negative of the change in spring potential energy. You do this integral, this is what you get, and you see there's U final and there's U initial. So there's the expression for the spring potential energy. Okay. So the spring potential energy is 1/2 kx squared. Okay. What does this expression say? The stiffer the spring, for a given amount of stretch, you're storing more energy. Okay. You stretch a spring, and the stiffer the spring, the more energy you store. Okay, we learned this last time. We sort of mentioned this last time. So let's say this is an object. You lift the object up vertically. You've done work on this object. And what did you do? To do work, you had to use energy, and you transferred that energy to this guy. Remember this guy, now you have stored energy mgh in it. Okay, so again, I'm lifting this object. To lift this object, I did work. Okay. To do work, I needed energy. So work was a mechanism for transferring energy from me to here. Okay. All right. So conservation of mechanical energy. Mechanical energy is potential energy plus kinetic energy. Okay. So here's the statement. As long as only conservative forces are doing work, as long as only conservative forces are doing work, is conserved. What does conserved mean?
So constant.
Very good. All right. Is friction a conservative force? No. So if friction is acting in your system, then mechanical energy is not conserved. Okay. Does normal force do any work? No. So if normal forces are present, you're not bothered. Okay. What you don't want is non-conservative forces doing work. Okay. If somebody is pushing a cart, is mechanical energy conserved? No, that's a non-conservative force. Okay. All right, so that's the statement. So let's say you drop this object, or this object slides down a slide, frictionless slide, at all locations, kinetic energy plus gravitational potential energy will remain constant. Okay. Okay. So, okay. So at every point, the sum of kinetic and potential energy is the same. Okay, so here's another example. Again, when is this true?
When there's no friction.
When there's no friction. Okay. All right. Or these things don't have jet packs and stuff like that. When when non-conservative forces are absent. Okay? So the principle of conservation of mechanical energy allows us to solve problems that would be quite difficult to solve using Newton's laws. Okay, so if you use Newton's laws and try to calculate the speed of this guy along those paths, that would be very hard to do. Okay, okay. Non-conservative forces. Okay. What does that mean? That the work done by these guys, when you do this line integral, that is path dependent. Yeah. All right. How many non-conservative forces are there? I'm sorry? Yeah, many non-conservative. Okay. Yep, there you go. All right, so we have to deal with those. Okay. When non-conservative forces, such as external forces or friction forces, act on a system, mechanical energy of the system changes. Okay. So this is non-conservative force. When non-conservative forces act, mechanical energy changes. So if your non-conservative force does positive work, your mechanical energy increases. If your non-conservative force does negative work, your mechanical energy decreases. Friction forces always do negative work, and your mechanical energy decreases. So when you apply brakes on your car, you're doing negative work, and your kinetic energy is decreasing. Your mechanical energy is decreasing. Okay? So non-conservative forces change mechanical energy. Okay. The work done by friction force is easy to count for. So it's the friction, negative of the friction force times the displacement. Okay. So we've separated the work done by friction force, and this is other non-conservative forces, such as you pushing on a cart and stuff like that. Okay. Yeah. We'll bring this to that side. What does friction force do when you apply brakes on your car? What did the friction force do?
Pads press on the rotors,
Mm,
which
but-
creates friction and slows down the car.
And what was the ultimate result?
Create force in the opposite direction.
It created force in the opposite direction. What happened to your kinetic energy?
That transferred into heat.
Heat. That's right. Mechanical energy got converted to heat. That's what friction does. Okay. So the work done by friction force got converted to thermal energy. Okay. The point is, energy is not destroyed. All is done is converted from one form to another. Okay. Mechanical energy is easy to keep track of. Thermal energy is hard to keep track of. Okay. So the heat got transferred to heat. What happened to the heat? It eventually got dissipated into the atmosphere. Very hard to keep track of. Okay. All right, so the work done by friction force got converted to heat. Okay, if you could keep track of all the energies for an isolated system, change in mechanical energy plus change in thermal energy plus change in internal energy, the sum of all those changes would be zero, because the total energy of this isolated system remains constant. That's the statement. That's the energy of conservation statement. Okay. Okay, so here's a model. Here's a mass attached to two springs. So this is the equilibrium position. Okay, so meaning if in the equilibrium position, if I let it be, then it'll stay at rest. What happens if I push it this way? What will the system do?
Attempt to restore its equilibrium
Yeah,
position.
so if you push it this way, this spring will pull on it, this spring will push on it. It'll try to bring it back to this side. If I push it to this side, this guy will push on the right and this guy will pull back on the left. Okay? So if you look at the potential energy of this guy when he's over here. This is the potential energy curve. Okay? So at this point, the potential energy is high. If the object is moved to the right, the potential energy is high. Okay? In fact, this will be a parabola. Okay. So when you're on the left, the force is to the right, and when you're on the right, the force is to the left. It turns out, well, how large is the force? It turns out the force is the slope of this tangent line. That's the magnitude of the force. Okay? So the force, it turns out, is negative du by dx. U is the potential energy. Okay, here du by dx is positive. That's the slope of the tangent line. And negative of that is the force. The force is to the left. Du by dx is negative here. Negative of negative is positive. The force is in the positive direction. What is the equilibrium point? What does equilibrium point mean?
Force applied is 0 in both directions.
So du by dx is 0 here. Okay? And the force on this guy is 0. Okay? The system is not applying any force on it. Okay? So you see that local minima point of the potential energy curves are equilibrium points. Okay? Okay. So the force, the conservative force is given by negative of the spatial derivative of the potential energy curve. Okay? So the conservative force is equal to the negative derivative of the potential energy curve with respect to position. Okay? So we saw that with conservative forces, you can associate a potential energy function, and the potential, from the potential energy function you can calculate the force. Okay? So they both contain the information about the potential energy curve. The potential energy function contains information about the force. Okay? If you know the potential energy curve, you can calculate the force everywhere. That's the formula used to calculate the force. Okay? So if you want to describe the behavior of a system, giving the potential energy curve tells you all the information you need to know about the system for analysis. Okay? So if the system were there, the force would be du by dx is negative, the force is to the right. If the system is here, du by dx is negative, the force, du by dx is positive, the force is to the left. If the system is at this location, du by dx is 0, that's an equilibrium point. How about this? If the system is here, what is du by dx?
0.
0. What is the difference between this equilibrium and this equilibrium? All right. So you guys understand what I'm asking?
Is it 2q?
I'm sorry?
Is it 2q? You mean the difference between the two equilibrium points?
Yeah, what is the difference between this guy and this guy?
So it'd be negative q to 0 and 0 to q, so it'd be 2q.
All right, so let's make sure we understand this. Okay, so this equilibrium, let's say I go to the right of this equilibrium point. At this point, du by dx is positive. Negative of that will give you a force in this direction. If I go to this point, du by dx is negative. Negative of that will give you positive. The force is in this direction. If you move away from this point, the forces that come into play are restoring forces. Let's go over here. If I move to the right, du by dx is negative. Negative of negative is positive. The force is in that direction. You move away from this point, the forces are taking you further away from that point. You move away from this point, du by dx is positive. Negative of that is the force is in that direction. You're moving away from that point. This is what is called an unstable equilibrium. This is a stable equilibrium. Yep. So du by dx, so at this point du by dx, it's negative and increasing. Second derivative is positive at this point. For stable equilibrium, d square u by dx square is greater than 0, and du by d square u by, okay. So for stable equilibrium, it's a local minima, and for unstable equilibrium, it's a local maximum. All right, so f was du by dx. This was in 1 dimension. In 3 dimensions, okay, f is the negative gradient of u, the potential energy function. Okay, have you guys seen the gradient function? Does anybody know that? Okay, you are in Calc 3, Calc 2, 3. Okay, who has seen the? Well, I guess most of you haven't seen the gradient function. Okay, so let's quickly do the gradient function. Okay, so let's say here's a function x, y, z. It's a scalar valued function. What does that mean? At every point, it spits out a scalar number. This could be the temperature, for instance. Okay, so let's say you can talk about what the temperature is at every location in this room. Or it could be a furnace. What is the temperature at every location in the furnace? Okay? So I'm going to give it a, I'm just going to give it a, okay, just for, okay, so just as an example, x, y, z. Okay, so you can calculate the value of this function at every location. Yeah. So if it represents the temperature, you can calculate the temperature in every location. Okay, so actually, let's call it temperature. Okay. Now, you can ask the following question. Okay, in what direction does the temperature increase the fastest? Is that a valid question? Okay. So you ask, in what direction is the temperature increasing the fastest and at what rate? And that's what the gradient function will give you. So the gradient function is a vector. Okay. And here's how it's defined. Delta t by delta x. You guys all understand partial derivatives? Okay. Who doesn't understand partial derivatives? Okay. Do you understand derivatives? So you understand partial derivatives. Okay. You'll understand partial derivatives in a second. Delta t by delta y j plus delta t by delta z k. What this means is, what is the temperature, how is the temperature changing as you travel parallel to the x-axis? That's what the partial derivative means. What does delta t by delta y mean? How is the temperature changing as you're traveling parallel to the y-axis? Okay, I don't know what delta t by delta z means.
How the temperature changes as you travel parallel to the z-axis.
There you go. Okay. All right, so how do you actually calculate this? So when you're calculating delta t by delta x, you treat these other variables as constant. Okay. So what is delta T by delta X? Help me out.
2x.
2
2x
X
times y cubed
cubed
times
z.
z to the fourth.
Okay. Keep going. I'm sorry?
It'd be x squared, 3y squared, and then z to the fourth.
Mm-hmm.
And then it would be x squared times y cubed times 4z cubed.
X squared times y cubed times 4z cubed to the power k. All right, so the gradient of the temperature tells you in what direction the temperature is changing the fastest, and it gives you the rate of change of temperature. Why the heck are we interested in that? Heat flows in the opposite direction. Okay, so you get the temperature gradient, and flow of heat will be proportional in the opposite direction. If this guy was pressure, gradient of pressure, wind blows in the opposite direction of gradient of pressure. If that guy was a potential energy, the force is in the opposite direction of the potential energy. If that guy was a concentration of some material, diffusion will be in the opposite direction of the gradient of concentration. Okay? So gradient is a very important thing. If it's temperature, it tells you about heat flow. If it's pressure, it tells you about wind blowing. If it's potential energy, it tells you about which direction the force is acting and so on. Okay? If it's if it's a function of, it's telling you production of some material, the flow will be from in the opposite direction. Okay? And so on. All right. So you saw that. Okay, so this local minima are what kind of equilibrium?
Stable.
Very good. Local maxima are unstable. These are neutral equilibrium points, and so there's a whole infinitely many equilibrium points, and if you move from one equilibrium to another, it'll stay there. Okay. So those are okay. Stable equilibrium point. Here's an unstable equilibrium point. Okay. Okay. So these potential energy curves are very useful, I guess. So for instance, this room is full of diatomic molecules, and if you ask the question, so 78% are nitrogen and 21% are oxygen. So how far is the distance between two nitrogen atoms? Okay. So if you pull this nitrogen atom too far, what is this guy going to do? He's going to pull him back. If you push him too close, he'll push him away. Okay, so this is the potential energy curve. Okay, there is the equilibrium point. So this is the bond length. Okay, so you give a curve like that, and you know the bond length. What happens if you heat up the nitrogen gas? They'll vibrate. Okay. It'll rotate and all that stuff. So these potential energy curves tell you about the system, how the system will behave. Okay, so if you want to describe the behavior of this system, how this system might behave, all you do is throw this curve at somebody, and you've given a very important piece of information. Okay. All right, guys, we'll stop here. I will see some of you guys